Good morning, colleagues. I'm Alexander Kamensk. I'm from Perm, Russia, and this report is dedicated to the problem of natural vibration of thin-walled structures like shells or plates under the influence of the thermal loads. As we all know, a change in the stress state in these structures can lead to a change in their dynamic properties, like frequency spectrum. An excellent example of this is string musical instruments, where a change in tension of the strings alters their frequency spectrum. Actually, our main focus in this study is on the numerical simulation of how stresses affect the natural frequency spectrum of thin-walled structures. These stresses can arise from various sources, such as change in temperature within this structure. Specifically, we will examine this impact that temperature-induced stresses on the fundamental oscillation frequencies of shallow shells and three-layer plates. Sorry. Oh. Well, the first part of my presentation will focus on the mathematical formulation. The problem of natural frequency of a preloaded piecewise homogeneous body is based on the following variational equation. To take into account the pre-stressed state of the structure, it is necessary to consider the deformations, the strains like finite, as finite. They can be represented by the exhibited sum. Here, the matrix S is a quite large matrix, and it is not given here, but it consists from derivatives of displacements like vector S. To take, then the problem of natural vibration can be solved by representing unknown displacements in a specific form. This form is the product of two functions. The one of them is a function which depends only on the displacements field, and another one that contains time in its exponent. After substituting this interpolation into variational equation and performing some significant simplifications, we can obtain the equation for the vibration of a pre-stressed and pre-strained body. Here, the components that are reasonable for both pre-stressed and pre-strained point of maybe I can it's not okay. This component is pre-stress state, and this integral such a big refers to pre-strained state. Actually, the components highlighted on the previous slide, namely the sigma matrix, sigma zero matrix, and initial deformations integral, can be obtained from a preliminary solution to the static problem, this problem, of loading a body with temperature loads. The numerical implementation was carried out on ANSYS mechanical PDL software using the finite element method. The discrete form of the equations 5, without considering the initial deformation, is as follows. Thus, the object of the study are the three-layer plate and an isotropic shallow shell. The boundary conditions used in the task are described as follows. The letter C represents the clamped edges, and the letter F represents the free edges. Here is the comparison of the numerical results obtained with those method of the authors of the article presented on the slide. The problem of the temperature loading on the plate clamped on all sides has been solved. As you can see from the slide, there is a good agreement between the results. A three-layer plate was selected as the object of study where the influence of temperature stresses can be neglected because we use the boundary condition without any clamp. It was free edges of the plate. Two plate configurations were examined. The ASA configuration, aluminum, steel, aluminum, and SAS configuration, steel, aluminum, steel. The coefficient of linear thermal expansion of steel and aluminum differ approximately 2 times. From the graphs, it can be seen that the generated stresses field has a minimal impact on the first frequencies of this plate. Different variants of kinematic boundary conditions are considered, and they strongly influence the natural frequencies of the structure. Here are the results for a plate that is clamped on two opposite sides. You can see that it is beginning to lose stability as its frequency approaches to zero. The conversion of frequency to zero is only possible in a linear formulation, which doesn't accurately describe the processes near and after the critical zone. However, this linear formulation can still be used to determine the point of loss of stability and the critical load values. Here you can see that there are enough force discretization for, The following are the results for shallow shells. A special case is a plate with 0 ratio of the lifting height to the thickness, this ratio, h smaller. The nonlinear formulation of the problem allows us to observe the critical process. We can see that the plate loses stability much earlier than the shell, even with minimal raise ratio in this picture. Furthermore, after the loss of stability, the natural frequency of the plate increases. However, then there is a change in the forms of vibration, that is, the second and first forms of vibrations change places. In this moment, you can see that first the frequency is raised, and after some point, it starts to decrease. Here you can see that there are enough force discretization for describing the critical zone. This slide shows a different type of boundary conditions where the shell is fixed at two parallel sides. We can see that the frequency changed more gradually than a fully grounded shell, which represented in previous slide. So finally, numerical studies have been conducted to assess the impact of the stress field generated by the temperature load on the natural vibration frequencies of plates and shells. Based on the results, it can be concluded that the temperature load has no significant effect on the natural frequencies of a three-layer plates without any boundary conditions, free boundary conditions. However, the effect arising from the boundary conditions are much more significant. If the plate is fixed at two or more ages, it starts to lose stability as the temperature increases. The study also investigated the natural frequency of isotropic unstable shallow shell. When the temperature reaches a critical value, the lowest frequency of the shell decreases. However, after the critical temperature, this frequency increases again. Thank you for your attention. I can answer your questions if any.